is going to be under. There is this, because you cannot run with that guy, right? And the other guy said he's pissed off. Okay, I'm going to go faster and I cannot go, right? Because I'm tied to the slow system, right? So he's going to hurt the system. He's going to hurt it. Especially the one is slower, because it's going to consume lots of power. It's going to get hot. It's going to get hot. I mean warm, not hot. It's going to get warm. It's going to get warm. And it's going to dissipate more power. It's going to be a problem. So the perfect condition is IC0, right? But that one doesn't happen. It's the perfect match to find the IC0. But this one is a no-load circulation current. It's the no-load circulation current. They're smaller than that. Now, let's close the switch, S3. We want to see how these generators they're gonna share the current. So let's forget IC and call this one IA or IA1. I call it IA1. IA1, IA2, and this switch is closed and this is the IF. And let's call this voltage VT. Right? This is a very simple circuit to solve it, right? First, I want to go through this one, and after that, I want to show you the real system, how they are. So here we should write the 1 KVL here. Let's just start to write the equation. One equation is VT is equal to what? IL times this, right? Let's write the equation. VT, and these are all phasors, is equal to ZL IF. Right? Another equation is IA1 plus IA2 is equal to IF. Right? This is the second equation. Now, 1 KVL here, we said it's the generator. EAF1 is equal to VT plus RA1 plus JXS1 IA1. And the second one is with AF2 is VT plus RA2 plus JXS2. Right? We have these 4 equations to solve it. If you solve this equation, IA1 is going to be EAF1 over Z. Oh, let's put it there. We call this one ZS1. Let's call this one ZS2. ZS1 and ZS2. It's going to be ZS1 plus ZL plus ZS1 ZL over ZS plus EAF1 minus EAF2 divided by ZS1 plus ZS2 plus ZS1 ZS2 over ZS1 plus this. IA2, I'm going to leave it with you guys. You can guess what it's going to be. What it's going to be? Yeah, you need to find.
What's ZS?
Yeah. Oh, ZF. Sorry, ZF.
Better cancel out.
Yeah. I need to go and calculate. This was like 20 years ago. I have to go calculate this one tonight myself to come back and tell you what it is.
It looks like they're in parallel, right? So
Yeah, no.
yeah, plus the other.
Now, keep this this one now. I'm gonna come back to fix this window because I have to go write the equation, calculate that one. Give me for Thursday. Remind me to correct this one. But we don't use this situation. I'll tell you why we don't use it. It's too much. You know, I'll tell you how to solve it. This is one example. But remind me to tell you what's this one. You know, I don't want to put anything here. It says VS. I need to calculate this from that. So IA2 you can, let's say you know what is this one. IA2 you can guess. What's going to be?
Similar, but replace one with the second.
Can you tell me what's this?
IC.
It's similar to IC, right? Still think about it, you know. Then you have the both load, you know, these two you're not going to match exactly, right? Part of this, let's say we have a 20 amps here, right? If we have a 20 amps, this one is giving us 11 amps, this one is giving us 9 amps, right? So basically it's like that. This one is giving 10 and this one is giving 10, but there is a one current circulation here, right? So 1 plus 10 is going to be 11, and 10 minus 1 is going to be 9. So the better match these two they are, the less number this one. This is a circulation current under load condition. This is circulation current under load condition. If they are perfectly matched, both of them they have the same voltage and the same phase, right? If they have exactly the same voltage and the same phase, this one is going to be how much? 0, right? But that one doesn't happen, you know, it's very, very difficult to happen. You know, they're smaller, the better. So this is circulation current under the load condition. Circulation current under no load condition. So I'll figure out that one, you know, next Thursday I'll tell you what it is. Now the last one is Vt times 1 over Zs1 plus 1 over Zs2 plus 1 over ZL is going to be equal to EAF1 over ZS1 plus EAF2 over ZS2. To go over one example here. So these are how you can calculate the, if you want to calculate the power of this one, how you can calculate it now? You have the EAF, right? And you have the IA. You say EAF, IA conjugate is going to be the power is coming from there. Give you how much P is giving you, how much Q is giving you, right? The same thing for this one. You can calculate how much P, how much Q they are giving you, right? Let's go through one example. There is one more thing that I want to cover today, hopefully. Let me continue a little bit more, and after that I go over the example. So usually this is like a circuit tour. You know, this is not a synchronous machine. You know, if you look at the paralleling for the synchronous machine, they are like this. Can you explain this one first? This is a frequency versus power for a synchronous machine, right? If it's an ideal generator, what's going to happen? Frequency is going to be like this, right? Whatever power you're taking out of the generator, the frequency is not going to change. The generator is solid, rotating a fixed speed, right? Don't make a mistake. If the frequency change, let's say frequency was 60 hertz, become 50 hertz. It's not going to change that much. But still, the machine is a synchronous machine, right? It was rotating, for example, 60 hertz, 3600 RPM, right? Now the frequency is 50 hertz. I don't know, it's whatever you calculate. It's going to be, for example, 3000 RPM, right? You need to go calculate that. My point is, the machine is still synchronous, right? You know, you can say how much is the speed of the machine based on the frequency, right? But you know, there is no perfect generator, perfect machine. When you increase the load, the speed is going to drop, right? So when the speed drops, what's going to happen? This is a real machine, right? Frequency, we call this one F0 or no load frequency. No load frequency usually is the perfect frequency, 60 hertz, 61 hertz, something like that, right? And for example, this is a P full load. This is going to be F full load. So the frequency changes from no load to full load. The less change, the better, right? If the change is 0, it's perfect, right? It's perfect. But we don't have a perfect case, you know? They go down. Now, let's say put two of these generators in parallel, right? I have a one load, again like the system I have here. I have a generator 1, generator 2, and I have a load here, right? I'm going to put them in this curve, like this. Let's call this one P1, this one P. You can put it all on one axis if you want. There's no problem with that. And this is the frequency, right? This is the frequency axis. For example, this machine has a frequency like this. Sorry, it has a characteristic like this, right? And for example, this machine, I'm going to make it really bad, you know? So this is a very bad machine. See how much the frequency is dropping, right? So we have two machines, they are parallel, working together, and they are sharing this much power. This is a D load, right? This is a load character. I shouldn't say P load. This is a load. Let's call it load. This guy is going to give me, call this one P1. I don't know what to call it. PG1. I call this one PG1. And this one, let's call this one PG1 here, and this one PG2. This one is going to give me P1, right? And this one is going to give me P2, right? So P load is going to be P1 plus P2, right? If the load changes, for example, it will come, oh, what frequency the system is working with? Can you tell me what's the frequency now the system is working? Yeah, this one is giving me P2, this one is giving me P1, right? And they are parallel. They have to work with the same frequency, right? This is the frequency system is working, right? Now, if the load changes, let's go to the second. This is the first condition, load one, condition 1, right? Now we go to load condition 2, right? So we'll come here, for example. This is a load 2. How is it to change? The frequency is going to come here, right? This one is going to give you this much now, P prime 2. This one is going to give you P prime 1. Basically, I increase the load. Which one is going to give you more power? If they're two exactly identical, they're going to give you, for example, you have a 10 kilowatt 5 and 5, right? If they are not identical, like the one I have on the board, which one is going to give you more power? Which one is the better one? So for example, in this case, the one, I think, I think the one on the right side maybe is the better one, right? So that one is going to give you more. If you increase 10 kilowatt, so 7 kilowatts is going to come from the right side, right? 3 kilowatts is going to come from the left side, right? So this is a very, very common characteristic for generators. They call it group control. They use a group control because there is a group here. You know, they can change the frequency based this one. If you go check any power system book, you know, the book you had for the last quarter, go toward the end. There is an AVR system and there is a generator system. You know, go look at it. You can see a little bit of this kind of thing, like a group control. If you want to learn more about it, you know, we're not going to talk more about it. But if you want to learn about the dynamic of the system, all this, I'm not sure what course is the control course you guys have. You have this block diagram. I don't know. You go to the root locus. You go to the 171. If you go look at that chapter, I can go check the book. I'll tell you which chapter it is for next class. You can see there is a block diagram for system, control block diagram. All those PIs, like the governor, all those kind of things. You can model the whole system with those kind of things, and you can control the power. When you have several generators connected in parallel, you can use these control loops to control. See, this is a very simple thing. I said it here on the board, but in reality, here it's much easier to change the frequency and those kind of things. And usually, these changes is very, very small. have you measured the frequency of the grid? It's not perfectly 60 if you have accurate measurement. It does change at any time, but not at, for example, 59 or 61. It's going to go maybe in the third digit or the second digit of the frequency. Maybe it's a 60.05, 60.06, 60. I don't know, 009. You know what I'm saying? There's going to be some changes, but it's usually after the second digit, not the, even the second digit is lost, you know. You have to have a big load, very, very huge load to change the frequency for that one. This is a concept of paralleling based on this characteristic. Now, because this is only work for 2, if you want to put it in the same graph, you can put it this way. For example, this is a 1 and this is a 2. This is a G1, for example. This is a G2, right? And so if you want to see how much load you have, this is okay. They're going to work somewhere here, right? The same frequency, right? This one is going to give me this much, this one is going to give me this much, and this is the frequency, right? If I have 3 of them, for example, this is the G3. This one is going to give me this much, right? If you want to put them all on the right side, you know what I'm saying? This looks better, you know, this is a little bit nicer for just, you can put for 2, not more. But if you have a 3, all the characteristics you plotted here, so based on what frequency you are, you're going to have the same, you're going to have the same frequency but different power. We'll go over one example. Let's start with this one. I think it's easier. Let's go with the example for that one. Let's see, do I have an example of this one? Yeah, let's go here. It says we have a 2 generator which are connected in parallel and they have this characteristic. Generator 1 is a 700 kilowatt generator. 700 kilowatt generator. The F no load is 50 hertz, and F full load, FF, I call it FF, is 48.5 hertz. Generator 2, again, is 700 kilowatt, and F no load is the 50.5 hertz, and F full load for this generator is the 48 hertz. First we want to know if PL is a 1200 kilowatt, how much is the P, G1 and PG? How they're going to share the load. The B, what is the PL max? Let me say this way. What is the PL max? What's the maximum load we can support without overloading the generator? Without overloading the generator. Let me explain here. This is the rated power of this generator, right? When I'm saying without overloading, what does it mean? None of them should give us more than 700 kilowatt, right? And you can see here, these two generators, they're not exactly the same. You can see the thing. So, for example, one of them is going to be 700, one of them is going to be 500, for example, kilowatt, right? If you want to make the 500 kilowatt to 700, the one is 700 is going to go to 800, right? So, we are saying this part